Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the max profit with K transactions. This is a pretty difficult question, but it's also one of my favorites. Now, we're going to solve this question using dynamic programming, and before we jump into it, let's just clarify exactly what it's asking us to do. Basically, we're given an array of integers, like the one that I have in front of me here, 5, 11, 350, 60, 90. And then we're also given an integer value, k. In this case, it's going to be k equals 2. And the array represents a bunch of different prices for a single stock on different days. So for instance, let's assume that Algo Expert were a publicly traded company. These numbers here in this array would represent the price of one share of Algo Expert stock on different days. So let's say on day 1, one Algo Expert share would be worth $5. On day 2, it would be $11. Day 3, $3, and so on and so forth. And then the integer k represents the amount of transactions that you as an individual are allowed to do. A transaction is defined as buying a share of stock and then selling it. And so we want to know what the max profit is that we can get with k transactions given these stock prices. One last thing, we have to note that we can only hold one share of stock at a time. So meaning that if we can only buy one share at $5, for example. We can't buy 2 shares. Similarly, we can't buy a share at $5 and then buy another share at $11 without selling the first share. And one transaction consists of buying the share and then selling it. Awesome. So let's get into this example. Turns out the solution to this example, the max profit you can get here, is going to be to buy at $5, then to sell at $11, then to buy at $3, and finally to sell at $90. And so here, the sort of total profit would be $93. $93. Because you get $6 from buying and selling at 5 and 11, and then you get $87 from buying at 3 and selling at 90. So as I mentioned before, we're going to solve this problem with dynamic programming. So like most dynamic programming problems, we're going to be building a table that's going to lead to our solution. And in terms of coding, this table is going to be represented as a 2D array. So what we're going to do is we're going to have in the columns of this table, we're going to have these prices of our stock. And in the rows of our table, we're going to have the number of transactions. So let me go ahead and erase these little things here, and let's build our table. So on the side, we're going to put the rows 0 transactions, 1 transaction, 2 transactions. So in our table, we're actually going to build up these rows starting from 0 transactions all the way to k transactions. And now we're just going to kind of fill up our table. And first, for the sake of this example and the explanation, we're going to build it kind of intuitively, try to understand how we would solve this problem by hand or using just our mind, and then we're going to try to develop kind of an algorithm or a formula to solve it for us. So let's start filling out this table. If we have 0 transactions, that means that we cannot buy or sell a single stock. So naturally, the maximum profit we'll be able to make at any given day is going to be 0. So we'll just go ahead and fill out this first row, 0, 0, 0, 0. Now this seems simple enough, but this is actually going to be pretty important when we want to build up the rest of our array using whatever formula we come up with. Now, let's say we have 1 transaction, and we're on day 0 where the stock is worth $5. Well, we can't sell... We could buy the stock and sell it the same day, but that obviously doesn't do anything, so the max profit here is going to be 0. And it turns out that when we build up this 2D array, the first column is always going to be 0, because if we only have one price, we can never make a profit off of just one price, so we can go ahead and fill that out with 0 as well. Now let's move on to here, to this first row here, this second row here, and this second column. So we can buy the stock at $5 and sell it at $11. Simple enough. So here our max profit is going to be $6. Here we could buy it at 5 and then sell it at 3, but that would make a loss. Same for 11 and 3, that would be a loss. So our max profit is going to stay the same as before, 5 and 11. So we're going to put $6. Now we move on to this point. Now here we could get $45 if we were to buy at 5 and sell at 50. We could make $39 if we bought at 11, sold at 50, or we can make $47 if we buy at 3, sell at 50. So the maximum here is going to be $47. Now we get to the 60. Again, pretty simple. Now we're going to make $57. We're going to buy at the 3 and sell at 60. So we'll put 57. And lastly, with the 90, $87. Now we get to the second row, or rather the third row with 2 transactions. And this is where it starts to get tricky. This is where it starts to become harder to do even by head. And that's where we're going to start to try to figure out a pattern that exists to relate all these values together. So on this first value here, we can still only buy one at 5, sell at 11. Recall that we're not allowed to buy 2 stocks on the same, or 2 shares on the same day. So our max profit here is going to be the same as it is above. It's going to be $6. And then we move on to this next one. Once again, here it's going to be $6. Simple enough. And now this is where things change. We're this 50. Here, not only can we make $47 by buying at 3 and selling at 50, but since we have a second transaction, we can also make $6 by buying at 5 and selling at 11. Recall that we cannot hold the stock that we buy at 5 all the way to the 50 if we want to buy another one at 3. Remember, we can only hold one share at a time, so if we buy a stock at 5 and we want to buy another at 3, we have to sell the stock that we bought at 5, we have to sell it before, so at 11. So here, we're going to make a total profit of 47 plus 6, which is going to be 53. Now we get to this guy here. So here, what could we do? Well, we could buy at 5 and sell at 50, and then buy at 50, sell at 60 or something. Or we could just do what seems to be the correct answer here, which is buy at 5, sell at 11, buy at 3, sell at 60. So now here we're going to have 63. Oh, and here this 56 should be a 53 if I'm not wrong. Okay, yeah, if I'm not mistaken. Okay, cool. So now we get to this final value, and we're going to try to calculate this value by coming up with some kind of formula or relation between this value and all the other values that we've built up. Because we can start to kind of notice a pattern here. Whenever we get to a specific column, so a specific day with a specific price, we notice that we really have 2 choices. Either we decide that we want to sell our stock at this price, in which case we're going to have bought it beforehand, and we'll make the difference between whatever we bought it at and whatever we sell it at. Or we say, no, we don't want to sell it here. And so if we don't sell our stock at a given price, then our max profit is just the same as the max profit on the previous day. Which in this case, the max profit on the previous day where we sold at 60 is 63. So once again, we have two choices. Either we sell at the current price, which is going to be 90, and we're going to have bought somewhere before that, or we don't sell at 90 and we just make the max profit of the previous day. So with that, we can kind of start to come up with a formula. I'm going to try to write the beginning of this formula or this relation down here. So imagine we call this 2D array or this 2D table profits. We could say profit, or profit singular, profit on transaction T. We'll call these transactions, so the rows will be called T, or will be represented by T. So profit at T and on day D, and these are the days, and the numbers are prices, but these are days, right? Or the indices represent days. Profit at transaction T and on day D is going to be equal to, we want to maximize this profit. So we want to say it's the maximum of either deciding to sell at this or not selling at this and taking the previous max profit. So it's going to be the maximum of two things. Number one is going to be, let's take care of this previous max profit, which is going to be profit at the same number of transactions on the previous day, D minus 1. This guy, profit of T at D minus 1, in our example where we're at here, is represented by the 63. Okay? This is the max profit that we can generate using the same amount of transactions, 2, on the previous day that we're at, which was here. So the previous day is here, and that's the 63. Now, the second thing that we want to compare to is going to be selling here. So if we sell here, what exactly is happening? Well, first of all, if we sell here at the 90, we're going to get plus, we're going to make $90, or in other words, we're going to make prices of D. For the sake of good order, let me just put an arrow that says that this array, our original array, is called prices, and our table is called profit. So prices at index D, this $90, we pocket it. So we're adding it to this formula. Now wait, this formula is not done. Prices plus. So what are we adding to prices? Okay, what are we comparing the 63 against? Well, if we sell at 90, okay, that means that we must have bought the stock at a previous time. So let's just assume for this example that we bought the stock at $50, okay? Then if we bought the stock at $50, then we would make, let's just write it here on the side, we would make plus 90 minus 50, but that's not it. We would make 90 minus 50, but since we're at 2 transactions, we would have to look at what is the profit at 50 with one fewer transactions, with 1 transaction, and that turns out to be 47. So we would actually add this 47, because we would say, when we were at 50 here on this day with 1 transaction, the maximum profit that we could make was $47. And so then we bought 50. We started using our second transaction. We bought 1 share for $50, and then we sold it for $90. And voila. So we have $47 here minus $50 plus $90. And I'm just assuming that the currency is in dollars. So this is just for one example, assuming that we had bought at 50. But maybe we don't want to buy at 50. Maybe we want to buy at $3. Or maybe we want to buy at $5. In fact, what we want to do is we want to find the point at which we can buy or the day at which we can buy that will maximize our profit, or that will maximize this value here that I'm circling. And so what this is going to be is it's going to translate into another sort of max comparison, which is going to be the maximum of, let me write it in parentheses. So here I'm kind of writing in pseudo math or pseudocode, the maximum of prices, or not prices, negative prices, the maximum of negative prices of X plus profit of T minus 1 X, okay? Where 0 is less than or equal to X, which is less than or equal to D. So let's explain that. Let's explain what exactly I just wrote here. The maximum, we're adding, in this number 2 here, we're adding prices on day D, which is $90 in our example, plus the maximum that we can get of profit T minus 1, which is one fewer transaction than where we're at. We were at 2 transactions, so we go one row above at 1 transaction. Profit T minus 1 of X minus prices of X. So on a given day X, we look at the profit that we could make with 1 transaction. Let's go with the example here at 50. With 1 transaction on day where the price is 50, we can make $47. Then we buy at 50, so we subtract prices X, which is 50. And then we add prices D, which is 90. And so X can be between index 0 and 0 inclusive, and D, but not inclusive, so up to this. So for this example here, for this 90, we're going to check the maximum on each of these days, on the day where the price is 5, the day where the price is 11, the day where the price is 3, 50, and 60. And so if we apply this formula, let's test it out. Here, the number 1 will just be 63. This guy, profit of T, which T is equal to 2, D minus 1, we're here. This is if we don't decide to sell for $90, we make $63. So that's one possibility. Possibility number 2, here, we're going to have prices of D, which is $90. So let's write it here. 90. And then we have the maximum of this stuff, where X is between 0 and D, with 0 inclusive. So let's write it out. For X equals 0, we have minus prices of X, which is 5. So minus 5 plus profit of T minus 1 X, which is here, 0. So minus 5 plus 0 equals minus 5. For X equals to 1, we have minus 11 plus 6. So minus 11 plus 6 equals minus 5 as well. For X equals to 2, we have minus 3 plus 6. So we have minus 3 plus 6 equals 3. For X equals 3, we have minus 50 plus 47. Minus 50 plus 47. So we have minus 3. And for X equals 4, we have minus 60 plus 57. Minus 60 plus 57 equals negative 3. And here we can pretty clearly see that the greatest value is this guy. all the others are negative. We have -5, -5, -3, -3. Here we have 3. So this is the one that we want. So here we're going to say 90. Here we're going to say 90 plus 3 equals 93. And now we can add in our array 93, which is indeed the answer that we came up with at the very beginning. And so there you have it. Our formula is kind of in action, working to find us the greatest profit or the maximum profit that we can do on any given day with a certain number of transactions. Now, let's try to kind of analyze the time complexity of how all of this works out. And by the way, this will become clearer and clearer as we look at the code implementation of the algorithm, in case something here is still confusing. But so let's move some of the stuff that we wrote. So let me grab all of this and let me make it smaller. And let me erase this to the side here. Okay, so in terms of time complexity, so we notice that we are building a 2D array. So 2D array is kind of always 2 for loops, right? So we have n columns where n is the length of our input array of our stock prices or the number of days. And then we have k plus 1 rows. K is our integer k. So our time complexity is going to be presumably time equals O of n times k. K plus 1 kind of reduces to k. Now, let's wait a second. Is this actually the time complexity? Or is our time complexity a bit different? Well, at every iteration in this 2D array, we are applying this formula here. And what does this formula here do? Well, it compares number 1, profit at transaction t and day d minus 1, which is just a constant value check, right? In the array, it's a value that we've stored. Or we compare that to 2 here. Prices at d, which is also a constant operation. We're just checking a value. Plus the maximum of some, stuff, let's just call this stuff, for x between 0 and d. So for x between 0 and d, we saw that for our example at 90 here, where we came up with the 93, we actually had to check x equals 0, x equals 1, x equals 0, x equals 3, x equals 4, right? Because we had to check, basically we had to reiterate through this entire array. And it turns out we're going to have to do this at every point when we do this, when we traverse our 2D array and when we build our 2D array. So it turns out that we're actually this O of nk is not O of nk at all. It's actually O of n squared k. And this is our actual time complexity of our algorithm right now with this formula here in action. Just in case you're not convinced, let's just repeat why that is. We are building a 2D array that has n columns. It has k plus 1 rows. The 1 in k plus 1, we can just drop it because it's a constant value. We multiply n by k to get O of nk time, but then for each of those O of nk values in the array that we're creating or that we're generating, we apply this formula, which itself has an O of n operation here when we generate this maximum of the stuff for x between 0 and d. So we get to an O of n squared k time complexity. Now, if you got to this point in an interview, you'd be doing really well. And at this point, your interviewer might ask you, can you do better? Before you even talk about space complexity. We'll get into that in a second. And the truth is here, you can do better. When an interviewer asks you that, usually it means, yes, you can do better. And so let's try to see if we can do better in terms of time complexity. Whenever you want to try to see if you can do better in terms of time complexity, you have to check if there's at any point in time where you are recalculating values. And while it might not be apparent here in the way we did this example, if you went through each and every one of these values that we generated and you applied this formula and you wrote down what we wrote down here, the x equals 0, x equal 1, x equal 2, you would see that we are redoing the same work. To show you this, let me just grab this here down here. Let me move it and let me make it bigger. This is what we did. This is kind of the O of n, the additional O of n operation that's responsible for the n squared here that we did to generate the 93. Let me just circle the 93 in a different color so that you know what I'm talking about. Now, let's just see what we would do if we wanted to generate the 63. So before we generated the 93, when we wanted to generate the 63, what would we do? Well, we would do something similar for the profit TD minus 1. It would be 53 here. So this 63 here would become, let's put it in another color, it would become 53. The prices D here, this would become 60, which is right here. We would sell at 60. And then we would apply this O then operation here thing. And here we would do, x equals 0, and we get the same thing, minus 5 plus 0. Minus 5 plus 0 equals minus 5. X equals 1, minus 11 plus 6 equals minus 5. X equals 2, minus 3 plus 6 equals 3. X equals 3, minus 50 plus 47 equals minus 3. And then we'd be done, because then we'd arrive here. So you'll notice that between this, which we do to generate the 63, and this, which we do to generate the 93, we're actually calculating 4 of the same values, the exact same values. X equals 0, x equal 1, x equal 2, x equal 3. We have them here too. X equals 0, x equal 1, x equal 2, x equal 3. The only new one that we calculated for 93 was this one. And so basically, we can actually store the maximum value that we get here. So this part, let me circle it. This part of our equation here, we can store it at every time that we iterate through the array. We store it. So for when we're generating the 63 here, with this stuff here in kind of orange, we would get the greatest value. This max here is this. It's 3. We store that. And then when we get to the 93 and we want to generate the 93, we just calculate the last one, the x equal 4 thing, which gives us negative 3. And we compare that to the stored maximum value that we had previously, which is 3. And we notice that, this 3 is greater than minus 3, so this is our answer. And so just like that, we've eliminated this entire O then operation and turned it into a constant time operation by just keeping this stored at every iteration. So to make this just a tiny bit clearer, when we're going to be generating maybe this 6 here, we're just going to calculate, when we calculate this max stuff here, the O then operation, we're just going to calculate at that point x equals 0. And we store that. That would be our maximum. And then we get to the second one. And now we do x equal 1, and we compare it to this previous one. And so at every point in time, we've already stored the previous max. And so this becomes an O of 1 operation. And our time complexity here, we can kind of erase the n squared, and it just becomes O of nk. And there you have it. Now, Once again, this is a difficult question. This might be confusing right now. I think it'll be a lot clearer when we get into the code implementation of the algorithm. But at this point in time, we have managed to solve the question in O of nk time. Now let's quickly dive into the space complexity before we move on to that code implementation. Space complexity, pretty straightforward. We're building a 2D array, n columns, k plus 1 rows. So naturally, the space complexity is going to be space equals, you guessed it, O of n k. Now wait, before we move on, if I'm your interviewer, once again, I'm going to ask you, can you do better? And so now we know that we're being asked that in regard to the space complexity. And yes, we can do better in regards to the space complexity. How? Well, oftentimes, and you'll notice this in a lot of other dynamic programming problems on the website, when you want to see if you can do better in space complexity, you have to go back to your formula, the formula that you're kind of using to build the array, and see what values you're using in this formula and what values you really rely on. And it turns out here, if you really notice carefully, we're only relying on values either on the current row that we're at, profit at t, right? We're calculating profit td, and we're looking at profit td minus 1, which is kind of the current row that we're at. Or here in our other O then operation formula that we turned into constant time now, this guy, we're looking at profit of t minus 1, so the previous row. But we're never looking at profit of t minus 2 or t minus 3 or t minus 4 or whatever. We're only ever looking at 2 rows, okay? 2 rows in our 2D array of k plus 1 rows. And so what that basically means is that there is some way for us to not store our entire n by k 2D array, but instead to only store 2 rows of n length each. And so if that's possible, which it is, then it would turn our space complexity here, which we have as O of nk, well, it would turn it into O of n, because the k would just turn into 2. We'd only store 2 rows, and we would drop the 2 and just say that our space complexity is O of n. And so I will try to explain how that works in much greater detail in the code implementation of the algorithm. I will first implement a solution in O of nk time and O of nk space, and then a solution in O of nk time and O of n space, doing this trick where we only store 2 rows. That being said, I hope that this conceptual overview was helpful. Like I said, this is a tough problem, but it's a really cool one. And let's dive into the code implementation now. All right, so our function max profit with k transactions is going to take in 2 inputs: an array of integers representing the prices of our stock, and an integer k representing the number of transactions that we can make. The first thing we're going to do is take care of the edge case where we're given an empty array of prices. In other words, no prices. So if the length of prices is a falsy value, it's 0, then we're just going to return 0. The greatest sum that we can, or the greatest profit that we can generate is 0. After that, we're going to start building our profits table, our 2D array. So we're going to initialize it by just filling it with zeros, or filling it with subarrays that are filled with zeros. So remember, each subarray has to have n columns, where n is the length of prices. So we'll say 0 for d in prices, d representing a day. And then we'll have this subarray, we're going to have k plus 1 of these. So we'll say for t in range 0, or the range just k plus 1, 0 to k plus 1. And t represents transaction. So depending on the language that you're writing in or coding in right now, you might have to declare this 2D array in a different way. This is a kind of elegant way in Python, but it should be fairly straightforward. Now, after that, we're pretty much going to start building out this 2D array. We initialized it at 0, or we filled it up with zeros, because that's very important. Recall that when we were building the table in the conceptual overview, the top row and the first column were filled with zeros, because if we have 0 transactions, the maximum profit we can make is 0. And if we only have one price, the maximum profit we can make is 0. And these zeros are important because they're going to help us build the rest of our array. So for the rest of our array, we'll iterate through it, and we'll say for t in range 1 up until k plus 1. Like I said, we filled out the first row, so we don't need to start from 0. And this is where we need to apply that trick that we discussed when we lowered the time complexity from n squared k, from O of n squared k, to O of nk. We said that we would store that sort of maximum thing, the maximum formula where x was between 0 and d, with 0 inclusive. Well, here we need to initialize this value. And so we're going to call it something like max thus far, and we're going to initialize it to negative infinity, or whatever the sort of smallest number in your language, in the language that you're working in, is. And that's going to be important because for the first comparison that we're going to do using this max thus far, this negative infinity is always going to be smaller than whatever it is we're comparing it against. So then after that, we're going to iterate for d in range 1 all the way to the len of our prices array. Once again, our first column is filled with zeros, and we don't want to touch that. But so for d in range 1 to length of prices, that's when we now update our max thus far in a constant time operation, because we've stored it previously, by saying max thus far is equal to the maximum of our current max thus far that we have, and profits at t minus 1, d minus 1, minus prices at d minus 1. So what does this mean exactly? Well, we're comparing our previous max thus far, the thing that we previously stored, to buying a stock on day d minus 1, buying a stock on day d minus 1, so we're subtracting that price on that day d minus 1. That's why we do minus prices d minus 1, plus the profit that we had on that day d minus 1, with one transaction less than what we're currently at. Profits of t minus 1, d minus 1, minus buying the stock. And once we have this max thus far updated here, well, then we can just say profits at t and at d is going to be equal to maximum of, either we just don't sell the stock on this day, so we take the previous maximum profit, which is just going to be profits, same number of transactions t, but on the previous day, or max thus far plus prices d. So just try to recall in the conceptual overview when we were calculating this for the example with 93, when we got to that 93, here, this 93, profits t of d, ended up being equal to 93. It was equal to the maximum of the maximum profit on the day before, which I believe was 63, or max thus far, which we had calculated to be equal to 3, plus prices of d, which was 90. And so we got 93. And there you have it. That's pretty much it. With this double for loop here, we've pretty much built out our entire array, and we're doing it in nk time, because our max thus far, because we're storing it, because we keep storing it and keep updating it, it's just a constant time operation. And so we don't end up with that O then squared k time complexity. And so just at the end here, we're just going to want to return the final value in our profits array, 2D array. And you can do that however you want in the language of your choice. So let's just add at the top here the space-time complexity analysis. So O of nk time and O of nk space. And there you have it. This is our algorithm. Now, let's dive into the same solution to this problem, except the one that reduces the space complexity to just O of n. So this is going to be fairly similar. We're gonna implement a similar, pretty much the same formula, but we're not gonna build up our entire 2D array. So we're gonna have the same edge case at the beginning, and then what we're gonna do is instead of declaring profits, we're gonna declare 2 rows. Okay, and for those 2 rows, what I like to do, for me, it makes sense to call them even profits, odd profits. Even represents when we're at an even number of transactions. Odd represents when we're at an odd number of transactions. So we're going to say even profits is going to be equal to, we initialize it at 0 again, 0 for D in prices. Remember, this is a row of length n or D, where D is the length of prices, the prices array. And then odd profits is going to be the same thing, 0 for D in prices. And now we just go into our double for loop. So for t in range 1, k plus 1, we initialize our max thus far. So we're going to say max thus far equals float negative inf. So here this is important. Now, because we only have 2 rows, okay, because we only have 2 rows, we're going to have to kind of swap these 2 rows as we progress into our array. Okay, because let's say we had 4 transactions. We're going to start with even profits is 0 transactions. Odd profits is 1 transactions. And then we want even profits to turn into 2 transactions, and odd profits to turn into 3 transactions, and so on and so forth. So what we're going to do to kind of simplify this, because it becomes kind of hard to grasp and to keep track of, we're going to say if t mod 2 equals 1, so if we're dealing with an odd number of transactions, okay, we're at an odd number of transactions, then current profits, we're going to declare a new variable, current profits is just going to point to odd profits, and previous profits is going to point to even profits. And then else, if we're at an even number of transactions, then current profits is going to point to even profits, and previous profits is going to point to odd profits. And now we're going to apply our second for loop and apply our actual formula on these 2 arrays that we just declared here, current profits and previous profits. So we're going to say for D in range 1 len of prices. This is the same thing as in the previous solution. We're going to update max thus far. So max thus far equals the maximum of max thus far again. This is the value that we've stored. Now here, obviously, since we haven't built up our profits array, this is going to be a tad different. We're still going to have this negative prices of D minus 1. I can even copy paste it here. But instead of profits T minus 1, D minus 1 here, we're just going to say previous profits, right? The previous row on D minus 1, or at index D minus 1. So previous profits basically represents profits T minus 1, the previous row, at 1 less transaction. And then current profits of D, so current profits on day D, current profits is our current row, profits T, right here, what I'm highlighting. So current profits D is going to be equal to max of current profits D minus 1, the greatest profit that we had the previous day, but with the same number of transactions, or max thus far plus prices, plus prices D. And you'll notice this is very similar to our formula up here. And voila, we're done. We literally have finished our for loop. And here we're going to return something. Now, before I go into what we return, let me just reiterate. What we ended up doing with this solution, all we're doing is we replaced this profits 2D array with just two rows, two one-dimensional arrays. And then what these one-dimensional arrays represent basically is previous profits, which gets assigned to odd profits or even profits depending on the transaction that we're at. Previous profits represents profits of t minus 1, the profits at the previous transaction, so one row above. And current profits represents profits at the current transaction, profits of t. And that's it. That's literally all we've done. So it complicates the code a little bit, especially this part. This is the really important part, the kind of the swapping of the two arrays. But at the end of the day, it's the same application of the same formula. And it greatly simplifies or optimizes our space complexity, especially if k is a huge number. If k is 2, then we've barely optimized anything. But if k is like 1,000,000, you can imagine in a hedge fund or a trading floor or something, if they were to apply this formula, well, you would turn, n times 1,000,000 into 2n, which would be a huge optimization in space complexity. Now, the last little tricky part here is for the returning. For the return thing, we're going to use a ternary operator. We're going to say return even profits of -1. So the last value in even profits if k mod 2 is equal to 0, else odd profits -1. And so why are we doing this? Well, we're saying if the number of transactions that we're given is even, that means that our final row is the even profits, and we return the final value in that. Otherwise, we return the final value in odd profits. So that's our algorithm. This is going to run in O of nk time as well, and it's going to run in O of n space. I hope that this was informative. I hope that this was helpful. Once again, I will reiterate that this is a difficult problem. It's a really cool problem, I think, because there's a lot of room to improve upon your solutions for it. But if you got to even the O of n squared k times solution that we went over in the conceptual overview in an interview, you'd already be doing really well. And if you got to, this far or even this far, well, then you'd be doing absolutely fantastically. I think it is important to really try to understand what's going on here, because you will notice that this is something that you can apply to a lot of other problems, especially in dynamic programming. Oftentimes, you can really improve the space complexity by doing these sorts of optimizations, by only keeping track of like 1 or 2 rows in your array, whatever your formula depends on. And that's that. So really try to understand this, and I will see you in the next video.